Good morning, everybody, and thank you, Chair, for your introduction. Wow. Okay, the purpose of my talk is to present these key encapsulation mechanisms based on QC-LDPC codes. Well, we are in the area of code-based crypto. I will be very fast here. Many of the basic concepts have already been recalled by Jean-Pierre in his keynote speech. Everything started with mechanisms using GOPA codes in the 1978 crypto system. And an important point is that besides quantum resistance, we also have algorithmic efficiency of these systems. And then in 1986, the writer introduced a variant in the syndrome domain instead of the code word domain, but they are two formulations of the same trapdoor. And using GOPA codes, these systems have resisted cryptanalysis for about 40 years. But on the other hand, we know that GOPA codes are large to store and quite slow to decode. So everything is starting with GOPA codes, but considering only the Hamming metric, there have been a lot of attempts to replace GOPA codes with other families of codes with the main purpose of reducing the public key size and improving the efficiency of algorithms. And okay, these are not all attempts, but there are many attempts that failed, resulting in security breaches, like GRS codes in the original data writer, the first proposal on quasi-dyadic codes, convolutional codes, the first proposal on LDPC codes, and the first proposal on quasi-cyclic codes. Then many other, and others. Many other evolutions stem from these proposals, for example, from GRS codes, quasi-dyadic codes, convolutional codes. And in my talk, we are focusing on an evolution following from LDPC codes and quasi-cyclic codes, resulting in the use of quasi-cyclic LDPC codes. We proposed for the first time in 2008, so they are now resisting cryptanalysis for 10 years. And an important point is that a new variant of QC-LDPC codes that are named QC-LDPC codes was introduced by Wisowski, and Barreto in 2012. Okay, LDPC codes have already been introduced by Jean-Pierre. They are capacity achieving codes under iterative decoding and allow random-based design. This is important for achieving very large key spaces. In principle, this sparsity of the parity check matrices could be attractive for reducing the representation of the keys. And these are features that make them interesting in mechanism data writer. However, there's an important security point to be taken into account. If we use a public code that is LDPC as well, then we are in troubles because the secret code can be exposed. And there are two main solutions to address this problem. The first one is to use a transformation matrix Q that hides the sparse matrix, the sparse parity check matrix, and of the private code into the public code. So we replace the permutation matrix that was used in Mechalis with a denser transformation matrix, and this was our proposal in 2008. The other solution is to use a private code that is defined by a parity check matrix that is denser, and it was called a moderate density parity check matrix as proposed by Wisowski, and Barreto in 2013. Okay, the first solution has some advantages and drawbacks. The main advantage is that iterative decoding is more efficient on more sparse matrices. But on the other hand, the multiplication by Q increases the weight of the error vectors that have to be decoded during decryption, and this is the main drawback. So one of the purposes of this talk is to address this problem by proposing improved decoders that fill this gap. Okay, we all know what a QC-LDPC code is. This is just a toy example. We have a parity check matrix that is one row of circular blocks. And in this case, the number of circular blocks is 2, denoted as N0. The code rate is N0 minus 1 divided by N0. And the column weight is DV equal to 3. The row weight is DC equal to 6. The most important feature of these matrices is that they are described by only one row, obviously. And here we have a storage size that increases linearly in the code length. That is the main advantage over classical random-like codes. And the code length is normally very large, but matrices are sparse. And we say that we have a QC-LDPC code when the column weight is in the order of the logarithm of n. Let me say less than or about 20 for the code length we consider. We say that there is that it is an LDPC code if the column weight is in the order of the square root of n. That is in the order of 100 for the code length we consider. Okay, for decoding these codes, classically iterative decoders named bit flipping decoders are used according to Gallagher, and they are well suited when we have no soft reliability information from the channel. That is the case we have in Mechalis. Okay, according to Gallagher, the bit flipping decoder definition is this one. The decoder computes all the parity checks and then changes any digit that is contained in more than some fixed number of unsatisfied parity checks. And using these new values, the parity checks are recomputed and the process is iterated again until the parity checks are all satisfied. So it is a very simple iterative decoder. Okay, these are the main contributions of this talk. First of all, we introduce a key encapsulation mechanism based on QC-LDPC code-based systems. Then we propose a new decoder that exploits the knowledge of the matrix Q to improve performance. And then we propose a reference and portable C implementation of the system. Okay, the functions of the CAM are very simple. To generate the key, we generate a secret H, a secret parity check matrix in the form of one row of circular blocks with column weight dB. And then we generate a random, non-singular, n by n block circular matrix, so Q is a quasi-cyclic as well, with a weight that is m much smaller than n, but greater than 1. And then we compute the public parity check matrix as L H equal to H by Q. So the private key is H and Q, while the public key is a systematic version of L. Key encapsulation is formed by generation of an n-bit error vector with weight T, and then just computing the syndrome of the error vector through the public code. And then the shared secret can be derived from it through some standard key derivation function. And the encapsulation starts with decoding. So with syndrome decoding, we recover the error vector starting from the public syndrome, the parity check matrix of the LDPC code and the matrix Q, and then we apply the same key derivation function to get the shared secret. Okay, concerning security, as already mentioned by Jean-Pierre, we have two big families of attacks, decoding attacks and key recovery attacks. The former aim at recovering the clear text from the ciphertext by performing decoding over a random-like code, while key recovery attacks aim at recovering the private key from the public key. The most important algorithms for performing decoding attacks are information set decoders. This principle was introduced by Brang in 1962 and then improved by Lee Brickel and Leon Stern in 1988-89. And then more recently, there have been great advancements in these algorithms. Modern information set decoding exploits the fact that the decoding problem can be translated into the problem of searching for low-weight keywords. And modern approaches exploit the Berkeley paradox for this purpose. And there are some references here, and other can be found. And there are also lower bound on complexity of information set decoding. So today we have quite good estimates of the complexity of these algorithms. However, we must take into account that an attacker could be provided with a quantum computer. So we know that Shor algorithm cannot be used for this purpose, but Grover's algorithm can be of some help. We know that Grover algorithm was designed to finding the roots of a Boolean function, and it helps finding one entry in an unsorted list of n entries in a time that is in the order of the square root of n. Okay, so we can apply Grover to information set decoding, and we have a reduction in the number of iterations, but this doesn't change the cost per iteration. So the attack complexity remains exponential, although we have some advantage in using Grover, and so it impacts the word factor of information set decoders. Okay, we use the analysis reported here by Levry in 2016, and just to give an example, if we fix the code length and the code dimension and increase the number of errors, we have that both without and with quantum computers, the attack complexity is exponential in the number of errors, But when we consider Grover, we have the blue curves, and as we notice, we have an important advantage over classical computers. So we must take this into account. Then, concerning key recovery attacks, we can still exploit information set decoding because the public code matrix L is still quite sparse, and so, as mentioned by Jean-Pierre, an ISD algorithm can be used for searching for the rows of L in the dual of the public code. And so, we have two expressions here for the worth factor of decoding attacks and for key recovery attacks based on decoding. And both of them depend on the complexity of information set decoding. Then, more recently, the new key recovery attacks have been introduced, exploiting decoding errors. They are built upon two facts. First of all, these systems have a failure probability of decryption that is not zero. And secondly, this can be estimated by Eve through observation of Bob's reactions. However, in our key encapsulation module, we use ephemeral keys, that is one-time keys, so these attacks cannot be applied. Okay, let's go into the description of the improved decoder we are proposing. Okay, decoding in these systems is performed over the public syndrome that can be expressed as E prime by H transpose. And E prime is a sort of expanded error vector. That is E, that is the error vector used during encryption, multiplied by Q transpose. So if we denote as phi the support of E, then we can express E prime as a sum of rows of Q transpose according to the support of E. And these rows are sparse, so their supports are likely to be disjoint or almost disjoint. And the error vector used during encryption is sparse as well, and so the total hanging weight of the expanded error vector is in the order of m by t, where m is the row weight of Q transpose and t is the number of intentional errors. So if we consider the integer inner product between E prime and any row of Q transpose, say QV, then if that row was not among the rows forming E prime, that product is likely to be very small. Instead, if that row was one of those forming E prime, then the product is large. And apart from this, like in a classical BF decoding, we can estimate E prime by computing the integer inner product between the syndrome and each column of H. That is, this S multiplied by H with this symbol, resulting in a vector sigma. And then by thresholding sigma, we can estimate E prime. So we can use this vector sigma that is used for estimating E prime into the first product and compute sigma, the integer inner product between sigma and Q. This results in another vector R over integers that can be thresholded to estimate E. So this is the main rationale of the Q decoder. It is very similar to the original bit flipping decoder with some modifications. So we start with the all zero error vector and with the public syndrome. And then at each iteration we compute these two integer vectors. Sigma, that is just the product of the current syndrome by the private parity check matrix, and then R, that is the integral inner product between sigma and Q. And then we can estimate the support of E by thresholding R. And then obviously we update the error vector and update the syndrome, and at the end we output the last error vector and the last syndrome. Okay, an important point for the performance of these decoders is the choice of the flipping thresholds. Okay, we can use combinatorial arguments to estimate the probability that one bit of E is one condition on the value of the product row. And then we can define a decision margin delta, such that the decision condition we consider is that the probability of that bit being 1 must be greater than the probability of the same bit being 0 multiplied by 1 plus delta. And by considering that these two probabilities are one the complementary of the other, then we can compute the probability, the first probability as a function of delta. And if we increase delta, we increase the number of iterations, but we reduce the DFR. And starting from this, we can compute the corresponding decision threshold as B, that is just expressed by this formula. So, since the probability of each bit being 1 conditional draw depends on the weight of the error vector, and the weight of the error vector depends on the syndrome weight, then we can exploit a lookup table populated with the pairs WB, and during each iteration we can start from the syndrome weight and search in the table the best weight that approximates the syndrome weight and get the decision threshold. So it is quite easy to manage in a practical implementation. Okay, so based on these estimations of performance and security, we proposed these choices for the system instances, reaching the security levels, the security categories proposed by NIST. So here you have all the parameters, and here we have the security levels. Please note that we used the security level with quantum computers as a reference for the security category. So if you look at the classical computer, at the security level with classical computers, they are much higher because we are trying to fulfill the requirement with considering quantum computers. And the public key size is n0 minus 1 by p that results, depending on the security category, in a total size between 3 and 22 kilobytes. Okay, then we developed an optimized implementation using efficient operations on circular matrices and avoiding the invertibility check for the matrix Q. This was developed in C language without any platform-specific optimization, and this is the NIST reference platform we used. Obviously, there are further optimizations that are possible, like using improved polynomial multiplication algorithms or specific architectural extensions or even hardware accelerations. Okay, this is these are the results of benchmarking with the reference implementation, and we observed that the total time required by LEDAkem is in the order of 50 milliseconds for the first security category, about 100 to 200 milliseconds for the second and third security categories, and between 300 and 500 milliseconds for the higher security categories. We can observe that increasing the code rate gives an advantage in terms of reduction of the execution time, but on the other hand requires longer key size. Okay, that's all. Thank you very much for your attention.